To finish, we're going to look at the second law of thermodynamics and the law of entropy. Here we have one object which is 50 degrees and another which is 20 degrees. And we have this diagram where there is more heat going from the cold to the hot than there is from the hot to the cold. Question is, can this happen? No, it can't. And this is the second law of thermodynamics. The second law of thermodynamics states that thermal energy cannot spontaneously transfer from a region of low temperature to a region of high temperature. In other words, you put a hot object next to a cold object, the cold object gets warmer, the warm object gets cooler. This is what happens. You don't get the hot object getting hotter and the cool object getting cooler. That just doesn't happen, and it would break the second law of thermodynamics. Let's recap what we've looked at before. This is a thermodynamic cycle. Remember that it expands during BC, there's lots of work done there, and it contracts from D to A, and there's less work done here. Compare. Well, the work from BC is greater than the work from DA, so in other words, the system does work. But where does this extra work come from? Where does this energy come from? The fact is, we have to give it energy to make these processes take place. The energy comes from the heating. It gives out a little bit of thermal energy, but it needs to take in a lot more thermal energy in order to be able to do some work. So the thermal energy transfer in ABC must be greater than the energy that's given out in CDA. And this is called a heat engine. So it's basically using heat to do work. On the other hand, this is giving out more thermal energy than it takes in. How does that happen? Well, if you look at the work done from C to D compared to A to B, it's more. So in other words, you have to do work to the system to be able to get this thermal energy to come out. So you look at AB expansion, that's a small amount of work. The CD contraction, that's more work because the pressure is higher. So what does it do with this extra energy? It basically changes some of the thermal energy that goes in during the process ABC and gives out a lot more thermal energy in CDA. And this is a heat pump. We get the heat to go from a region of low temperature to a region of high temperature, but we have to do work to get that to happen. And this is so we basically have to pump the thermal energy to a hot place. We have to pump it uphill, as it were. So the work done transfers the heat or the thermal energy. So basically it kind of pushes the energy uphill, as it were, from cold part to a hot part. And this is a way we can represent it graphically. This is the first case. This is a heat engine. Basically you show this thermodynamic cycle with a circle, and we have to draw the arrows to show the energy going in and out. Well, we know that it does work, and it takes in thermal energy from a hot source and gives out thermal energy to a cold source. So this is how we represent a heat engine. And likewise, this is a heat pump. You put in work to make the heat go from one place to another. So we put in work done, because the heat is taken from a cold source and put to a hot source or hot reservoir. Okay, the second law of thermodynamics implies that thermal energy cannot spontaneously transfer from a region of low temperature to a region of high temperature. Now let's look at a heat engine doing work. How do we get it to do work? We basically have to heat it and it will expand. So it gets hot and expands. When it expands, it does work to the surroundings. Now what? We want to keep on doing this, and it's not going to expand forever. It's got a limited size. So we have to make it go back again under low pressure, and we have to cool it down. We want to keep on doing this. So we need to make it go back again, which means that we have to cool this volume down. So some of the energy needs to be taken out and it will go back to its original position again. But in order to do this, we must throw out this thermal energy. We must make it escape. And when this happens, this energy gets degraded. It can't be used again. It gets lost to the surroundings. And then we can go back to stage one. And then we can keep on doing work. But it does cost us some thermal energy that has to be thrown away to a place where we can't use it afterwards. So the summary. A heat engine can do work, but some heat energy has to be lost to the surroundings to make this happen if we want it to be a continual cycle. In other words, there is no heat engine which is 100% efficient. You can't convert all the thermal energy into work. You must throw away some thermal energy. And here we have this heat engine here. So this thermal energy can do the work, but some has to be thrown out. So some heat must be ejected in a cyclical process. One way of looking at it mathematically is the thermal energy from the hot reservoir is equal to the thermal energy lost to the cold reservoir plus the work done. And it's a bit like an air cylinder. If you heat up an air cylinder, it expands and does work, but you must throw away some of the thermal energy if you want it to go back to its original size again. Likewise, a heat pump, to get the thermal energy to go from cold to hot, doesn't go there by itself. This is a violation of the second law of thermodynamics. We have to do work, and we can make that happen. So we have to push it uphill to the hot source. So a heat pump, heat travels from cold to hot, but only if you do work to help it. It's a bit like making a board roll uphill. It doesn't roll uphill by itself. You have to do work to push it uphill. And this is a bit like a refrigerator. A refrigerator takes heat from a cold object and puts it to a place where it's hot, like it chucks it out the back of the fridge. But you must do electrical work for this to happen. The second law of thermodynamics, it's impossible to build a cyclical heat engine that does not transfer some to the cold reservoir. Or in other words, it is impossible to make a heat pump whose only effect is to transfer heat from cold to hot. In other words, there's no perfect refrigerator. You have to do work. You have to plug it in. What are the conditions for a steam engine to work? You know our friend Thomas the tank engine. It's basically the same thing. You have to have a hot wire, which is basically the burning coal inside the engine. That provides the thermal energy. This turns into work, but it's not going to keep on happening. You need the cylinder to go back to its original shape, its original size again, so you must throw out some energy somewhere. So in order to get Thomas to work, you have to throw some of the thermal energy away afterwards. Otherwise, you won't be able to continue doing work. If Thomas is in hell. Well, if Thomas is in hell, and the fires around him are the same temperature as the source of energy in the boiler, he's not able to throw any heat away, which means he's not able to do any more work, which means if Thomas goes down to hell, he stays there. On a lighter note, when we have a power station, this is the same thing. We have a hot source, which is basically, in this case, it's a nuclear reactor that provides thermal energy to make the engine work. It's basically a turbine. And that does work, and that causes a generator to produce electricity. But you must throw away some energy. You can't keep on doing it forever. You basically, in order for this turbine to continue working, you must throw away some thermal energy. So you must have a cold reservoir, and it's basically the cooling towers, and you must throw some energy out to the cold reservoir to make this happen on a continuous cyclical process.